All right, here's part two where I'm going to do problems 6 through 10 from section 3 of the second practice test, the second redesigned SAT practice test. Here's the first 5 problems that I already worked through, and then problem 6 starts here. So in this problem, you're told that you have these two parallel lines here and asked to find the value of P, in other words, the x-coordinate of this point right here. Probably not a good idea to ballpark it and be like, well, it looks like it's definitely more than 4 because if 5 goes from here to here, 5 would be about here, 6, 7, I don't know, 8-ish. If I had to guess without doing any calculations, maybe I'd guess 8. But that's not a great strategy to use. A strategy that you will want to use is that recognizing that if you have parallel lines, they have the same slope. And so the slope tells you to get from this point to this point, for example, you go up by 2 and right by 5. So what that means is to get from this point to this point, you would go up by 2 and right by 5 repeatedly. So I start out at -4. If I go up by 2, I'm up to -2 when I go right by 5. And then if I get up 2 more, now I'm up to 0 and I go right by 5. So I've gone right by 5 twice. Started at an x-coordinate of 0. I guess I'm all the way up to an x-coordinate of 10. So my answer would be D here. Good thing I didn't just ballpark it and say that it looks like it's about 8, because apparently the answer is 10. Now, if you want to check your answer or calculate things more formally, you could, but I think this up by, over by thing works out about as well as anything will. Kind of drawing these triangles, you went up 2 and over 5. So there you go. There's a picture if you're really a visual person. Number 7. 7 looks overwhelming. It's not as bad as it seems, but it looks overwhelming. What you need to know is there's this rule that deals with exponents. There's a few exponent rules that will be really useful in this test. And one says that if you are dividing exponents that have the same base, you can just subtract what those exponents are. So x divided by x to the a squared power divided by x to the b squared power is really just x to the a squared minus b squared power. And that's using this rule that allows you to subtract the exponents. So what you are given is that x to the a squared minus b squared power is equal to x to the 16th power. Well, okay, if these things are the same, then their exponents must be the same because their bases are the same. So a squared minus b squared equals 16. How do you solve this thing? Well, you have two different variables, an a and a b. But fortunately, they gave you more information. They gave you that a plus b equals 2. So really what you have are two different equations, one here, and you want to solve. And there's a few different ways you can do this. The substitution method is what most people refer to. The clever solution with this specific problem is recognizing that a squared minus b squared is a difference of squares. In other words, it factors into this form. If you were to FOIL this thing all out, you'd get a squared minus b squared. And why is this helpful? Well, it tells me over here that a plus b equals 2. So really what I have is this a minus b thing times 2 equals 16. So a minus b is equal to 8. So it asked me, what is the value of a minus b? Hey, that's exactly what I solved for. The answer is 8. If you hadn't realized that kind of trick way and you did some substitution, it would be a little bit harder algebraically. I guess I can go through and do that. In case you didn't recognize that you could factor, and you were at this stage right here, what you could do is solve for one of the two variables, maybe a, and then solve for the other variable b. In fact, I'm not going to do that. That's going to be a lot of work. What you would do, just to give you an idea, is solve for one of the variables in terms of the other one. That's not right. So if you subtracted b from both sides of this equation, you'd get here. Then you could plug that in up here, so you'd get 2 minus b, that whole quantity squared, minus b squared equals 16. You could then solve for b. Be a lot of work algebraically. Then you could plug that in here and get a. And then if you knew a and b, you could subtract them to get this answer. It'd be significantly more work. So I'm pretty sure this is what the test makers had in mind. Number 8, the measure a in degrees of an exterior angle of a regular polygon. Okay, so if you know what an exterior angle of a regular polygon is, I suppose you have a chance. Turns out that there's a formula for it. But are you really going to memorize all the different formulas about interior and exterior angles of polygons? I mean, I don't know. Maybe you are. It turns out that all you have to do to figure out the exterior angle of a regular polygon with n sides is take 360 and divide it by n. So how would you know to do that? Who would possibly have that memorized? Well, here's kind of the picture proof of that thing. So if I have a polygon, so I don't know, let's start with a pentagon maybe. This is supposed to be a regular pentagon, but it doesn't matter which shape you use. An exterior angle is defined to be this guy right here. Or similarly, this guy right here. Or this guy right here. Or this guy right here. Or this guy right here. Those are all the exterior angles. And if it's a regular polygon, those guys are all the same. So how do I know that those are 360 over n? Okay, so imagine if you made this thing smaller and smaller and smaller. If you kind of slid this in here and slid this down, maybe you could see, maybe I'll draw one more really small pentagon here. You could do the same logic. And I'm trying to figure out all these angles right here, which, okay, it's a bad picture. You can't even see those angles there. But the point is, if you could collapse these all the way down to a point, to a single point in the middle here, sort of what the lines would look like, is you'd have one going up this way, one going off that way, one going down this way, one going this way, and one going this way. And so your exterior angles would fall here, 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 and here. Hey, that's all the way around a circle. A circle is 360 degrees. So then each of these exterior angles would be 1/5 in this case of 360. So the reason this formula works is kind of that little proof right there. There's other ways you can derive this same proof, this same rule. Maybe I'll show you one more, although I don't know how many you want to see in these short videos. What a lot of people do is they say, oh, if I have a 5, for example, sided regular polygon, I can split that up into 5 different triangles. Okay, so what if I wanted to know what this angle, maybe I need another color, is right here? Well, it's just the supplement of this angle right here. So if I could figure out this angle, I'd be good. I just do 180 and subtract that and I'd get this angle right here. So how can I figure out this angle right here? Well, recognize that this angle is the same as this angle. These guys are the exact same. And 2 of these makes this shaded angle right here. So instead of thinking about those 2, I could think about these 2, because those 2 are also the same. So if I add up those 2, I get this shaded red region right here. Well, what is the sum of these 2 angle measures? That would be this shaded region. Well, I got this triangle right here. And I know that the sum of the interior angles on any triangle is 180. And this one right here must be 1/5 of 360, because 360 would go all the way around. So this angle here is 360 over n, 5 in this case. So what about the sum of these 2 guys? Well, these would be 180 minus 360 over n. Let's see, 180 minus 360 over n. I could do some math to simplify that thing. But I'm not going to, because 180 minus 360 over n is the sum of these 2 angles, which is this shaded region right here. But I don't want the shaded region, I want this outside part. And hey, I got a straight line right here, so this and this must add to 180. This must be the supplement of this guy. So if I want to figure out this angle here, maybe I need yet another color. I could just say it's 180 minus the red shaded angle. It's 180 minus this 180 minus 360 over n thing. But wait a minute, 180 minus 180, those just cancel out. The negative goes over here, and we get the same formula over here, 360 over n. Anyways, if you happen to know that the measure of an exterior angle for a regular polygon is always 360 over n, then the problem becomes relatively easy. It says if the measure of the exterior angle of a regular polygon is greater than 50 degrees, so I need 360 over n to be greater than 50 degrees. In other words, I need 360 to be greater than 50n. Put differently, I need 50n to be less than 360 degrees. Say greater than or equal to? Greater than. Okay, so this is all right. So which value of n, what is the greatest value of n that will satisfy this equation? Well, if n equals 8, for example, this is 400. 400 is not less than 360. But if n equals 7, 7 times 50 is 350. And sure enough, that is less than 360 degrees. So the correct answer in this case is 7. Relatively easy if you know this formula. But I mean, how likely is it that the measure of an exterior angle formula is going to show up on an SAT test? I don't know. This is where it comes from, and this is how you would use it. Number 9, the graph of a line in the xy plane has a slope of 2 and contains this point. The graph of a second line passes through these 2 points. If the 2 lines intersect at this point, what is the value of a plus b? Okay, so if you want the intersection of 2 lines, probably the easiest way to do it is to come up with the equations of the 2 lines and solve them algebraically. You might be able to do this one by graphing, but I don't know. That's kind of a dangerous thing to do on problems like this because it often involves a lot of approximation. So let me try doing it algebraically first. If I have a slope of 2 and it passes through this point, I can use point slope form, which is this guy, which says you just plug in this point. Here's x1, here's y1, and here is m. So if I just copy everything that was given to me, I got y minus 8 equals 2 times x minus 1. Which is perfectly fine. You can leave it like this, or you can say y minus 8 equals 2x minus 2, and therefore y equals 2x plus 6. If I distribute the 2 through, and then I add 8 to both sides of the equation. So there's my first line. My second line, they don't tell me the slope, but they do tell me that it passes through the points 1, 2, and 2, 1. So I can calculate the slope. If I call this x1, y1, and this x2, y2, the slope is just the difference in the 2 y coordinates over the difference in the x coordinates. So y2, I guess I'm calling 1. y1, it looks like I'm calling that 2. x2, I'm calling that 2. And x1, I'm calling that 1. So if you subtract here, you get negative 1 for the slope of the red line. And then I can redo what I did here. Use either of these 2 lines. I got y minus y1. So y minus, I guess I'm calling this y1. So to be consistent, I'll use that again here. Equals m, which I calculated, times x minus x1, which is this one right here. So I got y minus 2 equals negative x plus 1. In other words, y, if I add 2 to both sides of the equation, is equal to negative x plus 3. So now I got these 2 equations. This one here, maybe this should be in a different color. This one here, and this one here, and I want to know when they intersect. Well, when they intersect, their x coordinates and y coordinates are the same, so I can kind of set those guys equal to each other. Say this y is the same as this y, so 2x plus 6 would have to be the same as negative x plus 3. So then I can solve this. I can add x to both sides of the equation, and I get 3x. I can subtract 6 from both sides of the equation and get negative 3, and that tells me that x is equal to negative 1. And if I know that x is equal to negative 1, I can plug that into any of my equations, maybe this one right here, and get y is equal to 2 times negative 1 plus 6. In other words, y is equal to 4. So I got x equals negative 1 and y equals 4. And the question is asking me, what is the sum of the x and y coordinates that they're calling a and b? Well, if you add up the 2 of those guys, you'd get exactly 3 right here. Wow, that's a lot of algebra. That's a tricky way to solve this problem. Are there better ways to solve this problem? Probably. Let's see what happens if we graph it. I bet we can narrow down like what coordinate or what quadrant the lines intersect at. And then maybe from that we can estimate what a plus b would be. So let's see. I know that the slope is 2 and it contains the point 1, 8. So when x equals 1, y equals 8, 1, 2, 3, 4, 5, 6, 7, 8. I'm talking about this point right here. And then it's got a slope of 2, so it goes up by 2 every time it goes to the right by 1. Similarly, it goes down by 2 every time it goes to the left by 1. So I guess something that looks, roughly speaking, like this. This is my line in blue here. What about my line in red? Well, my line in red goes through the points 1, 2, which is this point right here, and the point 2, 1, which is this point right here. So if I sketch that guy, I get something like this. I can't tell exactly where these lines intersect. Maybe you could if you drew it a little bit bigger and counted up a little bit more carefully. But what do we know about this point? It looks like it's got a very small negative x value. If I had to ballpark what this point was, maybe I'd say its x coordinate is negative 1 or negative 2, something like that. If I had to ballpark what its y coordinate is, I'd say that its y coordinate looks to be a little bit less than 5. Maybe it's in the 4-ish range. So then if I look at these answers, I immediately can rule out C and D. Right? Because if you add, clearly the y coordinate is more positive than the x coordinate is negative from my picture. So when I sum the 2 of those guys together, I'm going to get a positive number. So really I'm down to these two as my possibilities. If there was no chance I was going to be able to do all this algebra in time in the heat of a test, I'd at least have a 50-50 shot guessing between A and B. Perhaps if I drew this a little bit neater, I could figure out exactly where the points intersect. I mean, they do intersect at a really nice point, -1, 4. Turns out that this point right here is -1, 4. And so maybe if you drew this a little bit bigger and a little bit more carefully, the fact that they intersect at integer coordinates would allow you to figure it out directly and come up with 3. So if you're really inclined towards algebra, you can do it this way. I just think it takes a little bit longer. In summary, what I would do for this problem, and maybe you have to solve it to know what method you would use in the first place, which is kind of problematic, but I would solve this geometrically like this. All right, moving on. Number 10. Which of the following equations has a graph in the xy plane which y is always greater than or equal to -1? Okay, if you know what these graphs look like, this problem is really easy. It turns out that C is the answer. However, that's dependent on you knowing what these graphs look like. Really what's going on is we're starting with, this is a function transformation problem, or at least one way you can do this is a function transformation problem. If you know that the graph of y equals the absolute value of x looks like this, those are supposed to be straight lines, it's just not the clearest drawn straight lines, and that y equals x squared is this U-shaped graph, it's this parabola. If you know that you have these shapes right here, and I guess x cubed, I could draw that, although my picture might get really ugly, but that's sort of this shape here. If you know that those are your 3 starting spots, then you just have to think about what happens, how they change. If the x coordinate, if I add or subtract to the x coordinate, I'm shifting my graph left and right. Because the x coordinate is how far you are left and right on your graph. So it makes sense that if you change the x coordinate like I'm doing here, you're going to move your graph left or right. If I change the y coordinate, if I change what happens after this thing is squared or absolute valued to make up a verb, like I do here and I do here, that's going to shift the graph up and down. So in A, I start out with this V-shaped graph in red, and then I shift it down by 2. I get y equal, it should have been in red maybe. Maybe this should be dotted in red. I don't know, somehow so you can tell the difference. I get this graph here. This is y equals absolute value of x minus 2. If you know what the graph looks like this, then you can kind of think about it and like, wait a minute, the y is always greater than or equal to -1? No, this dips down to -2 right here. This couldn't possibly be my answer. Similar logic with B. B can't possibly be my answer because I start out with this U-shaped graph, which goes through the point 0, 0. But then I shift it down by 2, so now it goes through the point 0, -2. In other words, when x equals 0, y equals -2, that can't be my answer there. This never could be my answer because x cubed, the graph of x cubed, looks like this, roughly speaking. This is y equals x cubed. Mathematically speaking, the range of this graph is from -infinity to infinity. This thing goes as far down as I want it to go. So before you even consider the transformations, this -2, which moves it even further down, you knew that this couldn't possibly be the answer because you can get negative values out of this thing. So really C ends up being the only possible answer, and it's the right answer. What this does is it shifts your graph 2 spots to the right. So I start out with this graph in green that you can't even see anymore, and I shift the entire thing 2 spots to the right. So maybe there's 2 over there. It looks like this. Note that this thing is never below the x-axis here. So the y coordinate can never be -1. It's 0 or greater. It's the right answer. But that's all dependent on knowing what these graphs look like. You could also do it algebraically. You could just kind of try some things. I want to see if I can get a negative y value out of these things. I want to see if I can get a y value that is less than -1 out of these things. We'll try plugging in 0. Plug in 0 here. 0 minus 2 is -2. Oh, -2, that's less than -1. That ain't the answer. Try plugging in 0 here. 0 minus 2, same problem. Plug in 0 here, same problem. Plug in 0 here, you don't have that same problem because you first subtract 2 and get -2, but then you square it and you get +4. In fact, if you stare at this thing, the last thing that is done here is this squaring. And when I square a number, I can't end up with a negative number. There is no real number that when you square it gives you something that's negative. Worst case scenario, this is 0. And then I don't do anything after that. I don't subtract from it. So there's no possible way that I could get a number out of this for the y coordinate that is negative. As the graph shows, this thing never dips below the axis. But if you didn't know what the graph was, you could probably reason your way through it algebraically like that. Anyways, the answer to this one is C, and I think I'll end this video here.